So since I am really the last lecture, I would like again to thank the organizers. It was really very enjoyable event, and I learned a lot. I'm going to talk about thermal transport and electron hydrodynamics. So it is in the title. I am not sure what we are seeing, as you will see at the end. Is it really hydrodynamics? But actually, I think there is a connection. And first of all, I should begin by this paper, because first of all, this is the first paper in which it is discussed that there could be a link between electronic thermal transport and electron hydrodynamics. And it was thanks to this paper and Claudia Felser's visit to our lab that I was brought to this. Actually, this paper, I think it's now published, and there is a second paper by almost a few of the same authors on the samples coming from Dresden, from Claudia's lab. So Alexandre is here. The two papers, you can compare it. The first paper tells that actually WP2 is hydrodynamic. The second paper, actually the main message is that it's an open question. We cannot rule it out. But before going there, I should begin with something. Again, I hope that the first part of this talk, you will find it as a tutorial with open questions. It's not about research. It's very old, about T-square resistivity. How much do we understand it? And then I am going to talk about what we actually, thanks to this collaboration, learned. We didn't know that actually there is a T-square thermal resistivity. This actually I knew, but the whole connection with helium-3 physics, which is actually very interesting. People in correlated metals, even if the original Fermi liquid was helium-3, know very little about how transport works in helium-3. And actually, there is a hydrodynamic window. The whole question is, are we seeing that or something else? Or is it, do what we see, as Andy said, something that the end of the game can be explained by the Boltzmann picture or not? I think the question is still open. So I come from, okay, people are always, marked by the country of birth or the intellectual milieu in which they grew up. I grew up with heavy fermions. I did my PhD on UPT3, and even if I moved and worked on other systems, there are stuff where you go back to what you learned as a PhD student. And what I know is that if you have a heavy fermion, this is actually, Steve told about this, he cited Senthil, according to which actually Fermi liquid is a marvelous piece of physics of 21st century discovered too early, and this is an exotic state of matter. I would like to continue about this. One of the things that fascinates me as an experimentalist is that when you measure one thing, you can measure other stuff, you can guess. You see, you do very different experiments. For example, you measure the specific heat of your sample. If you have a heavy fermion, this electronic specific is very large. You can measure its Pauli susceptibility, or you can measure its resistivity. And in almost everything I have looked at, these things are correlated. And you have ratios. The most famous, and actually the most straightforward, is the Wilson ratio. Because here we are comparing two thermodynamic properties. This is magnetic susceptibility. So this is related to density of states. And this is electronic specific heat. And along different samples on a log scale, when you can change these guys by 3 orders of magnitude, these guys correlate with each other. Here, there is no paradox. This is thermodynamics, and normally you can calculate both of these things very easily. What is maybe a little more surprising is the Kadowaki-Woods ratio, because while a specific heat is something which is thermodynamic, the resistivity is a transport property. But again, Kadowaki and Woods were two experimentalists. They're there to make this plot. It was published in Solid State Communications 20 years ago. As far as I know, it works almost everywhere, even near a quantum critical point. And now there are a lot of debates, actually, if you go to the details, like do weakly correlated metals like these guys. So I guess Andy's system is somewhere here. So it's very difficult to measure because the A term should be very small. But you see, in palladium or platinum or nickel, people measure it. And the whole question is, are there 2 lines or 1 line? But from far away, you cannot find anything here or anything here. I have not seen anything in my life. And also, this.
Those 2 numbers differ by, those 2 lines?
They differ by a factor of 10, I think.
Of 10.
Yes. So but then there are ytterbium compounds which are heavy fermion, which have 11 electrons but on the lower line. So you see, at first Kadowakian-Woods point was that you have one line for a strongly correlated system, another line for weakly correlated system. But it became more and more fuzzy with years because ytterbium systems, which are F electrons, and some of even cerium systems are on the lower one. So, yes?
There must be some interpretational uncertainty as well, because you're actually comparing one component of a tensor with the square of a scalar. And so a lot of these resistivities are anisotropic enough that there's going to be some scattering.
Completely, you are completely right. Yeah, so first of all, I'm talking about in-plane conductivity. You know, take a strontium root rate, for example. For C-axis, it doesn't work. For in-plane, it works. So there are, and actually, I'm going to come back to this.
What would worry me more are some of these other compounds where there's decent level resistive anisotropy, but you don't really know how to define in-plane or not.
Yes. Yeah, so you are completely right. You know, when you go to the details, there are many questions which, but if you give me a metal and you have a t-square resistivity, you know, if you know the gamma, you check if these two numbers match or not. The same is true for thermopower. It's more complicated because you have a sign problem. You can have positive or negative, which was not the case for the three others. But it works also if you compare the two systems. And again, there are exceptions, but there are few of them. So you can put the same thing. Speaking about Fermi temperature, renormalized Fermi temperature, is that if you measure resistivity, a specific heat, or Seebeck, you are measuring basically a temperature provided that you have just of the order of 1 electron per atom, or a few electrons per atom, something like that. Seebeck coefficient is the only one which actually doesn't have any geometric factor. Actually, it is basically an intensive question, provided that you are far deep inside the degenerate regime, you are measuring actually the Fermi temperature of your system. Again, I am forgetting that the Fermi surface can be very complicated. You can have many pockets and particularly many different aspects. But what I'm going to talk about is this guy, resistivity. And this has a very long history before. You know, it was actually almost simultaneously and independently, and for two different mechanisms, it was suggested in the two sides of the Iron Curtain in 1937. So actually, I like the way Neville Mott talks about it, because it's again very hand-waving. The whole idea is that, you see, it's all about having the Pauli exclusion principle applied twice to electrons. If you are seeing two electrons scattering to each other, the phase space for this scattering should scale with kBt over EF for one electron and for the other. And at the end, it comes back to something where we can write it in this way, in the modern way. So we have the quantum of resistance, as Steve mentioned it. And then we have this factor. And then there is this thing which should be material dependent. It depends on Kf, and it depends on the cross-section of the two electrons, which can be something which you cannot know from first principles. Now, before going to my main talk, I just say that actually we don't really understand how does it work. Because this, if you take a dilute metal like strontium titanite, and you can really change the carrier density by 5 orders of magnitude, you can really go to a place where you don't expect to see t-square resistivity. Because if you follow your t-square behavior, as you change the carrier density by many orders of magnitude, you see that this slope is changing just because you are increasing the number of carriers, you are decreasing your Fermi energy. You see that this t-square regime is going to go to higher and higher temperatures. Compare the horizontal axis of these three panels, and the magnitude is decreasing. And if you put the number, actually you are going to meet the dense systems. So across AbO3 metals, these are perovskites. Only in a strontium titanite we can go to such a low density regime. But if you go to very high density, you are going to meet other systems, and you see that actually the value doesn't show any big discontinuity. This NC1 is the region where strontium titanite becomes single component. You have a single type of Fermi surface and too small to have any kind of umklapp. But still you continue to have this t-square behavior. And actually, if you do it in another way, so you extend the Kadowakian-Woods idea to dilute systems. So here are a bunch of systems where you have something like 10 minus 2, 10 minus 3, 10 minus 4 electron per atom. You extract the Fermi energy, and you plot again A as a function of this Fermi energy. You basically see that you don't see any notable difference. Of course, it's not universal, and there are guys who are below, there are guys who are above, but it seems that we should have a unique mechanism for the way this electron-electron scattering leads to dissipation. But this is not the case. Normally, people invoke two different mechanisms. One is what proposed by Buber, that you have two reservoirs. One of them is much more coupled to the lattice, which is where you should leak your momentum. And then you have a bottleneck, because the second reservoir, which is loosely connected to the bath, is going to lose its momentum to the other one. And this is why you are going to see your loss of momentum. The Umklapp, which is what is favored in the case of heavy fermions, just needs a Fermi surface big enough to provide the possibility that the final wave vectors minus the initial wave vectors gives you a wave vector big enough to be comparable to the lattice. So this can be satisfied in any system which has a Fermi surface, which is a decent site of the Brillouin zone, but not in the dilute systems. So it seems that actually, I'm not sure I know the answer. You know, to have a counterexample is graphene. In graphene, people believe that momentum is conserved when electrons are scattering towards each other. But the T-square term to be seen is rather small. It has never been observed, but at least on all bulk systems we know of, it seems that any exchange between electrons is taxed by the lattice. The lattice somehow electron-phonon coupling gives you rise to this T-square resistivity that I am not aware of any system, any bulk three-dimensional system in which you do the resistivity, you guess the magnitude of T-square that you want to see, and actually resistivity is completely flat. So this is why actually it would be interesting in the case of ultra-poor materials to look at them and see what's happening. And I want to mention something about strontium titanate. There are people who believe that this is not T-square resistivity due to electron-electron scattering, and they may be right, because phonon spectrum in a strontium titanate is strange, to say the least. So it is not completely settled. There is not a consensus that in STO what we are seeing is exactly electron-electron scattering. Yes?
Main question. You would expect not to see any T-squared in a translation invariant system. So you need to break the translation invariant. There would not be resistance.
Actually, yes, but I'm going to come back to this when I'm going to discuss helium-3. There is a T-square thermal resistivity in helium-3. And we come back actually. So
boundary of defects, or
because it's argument is about phase space. You see, this is an argument about phase space of your. So the phase space gives rise to something which shows itself in thermal conductivity, thermal resistivity. So it's not about momentum flow, it's about energy flow. So you are right that it is different. But I come back to this at the end of my talk, how Galilean invariance can be important or not. Okay, so you may forget the digression on strontium titanate. Let's forget that case and imagine that we have a T-square resistivity. It's mostly about Umklapp. But let's look at thermal transport. So I showed this. Thermal transport is more complicated, but conceptually it's very much like electrical resistance. So here I'm going to talk about electrons. So the other talk was about phonons, and here the key concept is the fact that at the Fermi-Dirac distribution, entropy is rare. You can forget all electrons besides those which are at the KBT thermal window near the Fermi surface. And actually, Lawrence Molenkamp is not here, and one of the actually very good papers he co-authored in 1990s in the context of mesoscopic system is what I'm going to show in the next slide, is the fact that actually, so you see, people who work on bulk materials, they use the Boltzmann formalism, and people on mesoscopic materials use the Buteker-Landauer formalism. But actually, there is an equivalence. So thanks to Mahan, who reformulated the Boltzmann formalism in Landauer's language, instead of putting a transmission factor, which is what people use in 1D, you can take what is called transport distribution function, which is a material-dependent property. Density of states, the velocity, and the scattering time. So this depends on the details of your bond structure. But let's put all of them as some number which is energy dependent. Then the essential comes out. When you measure electric conductivity, you have a quantum of conductance times something which is the derivative of the Fermi-Dirac distribution. Basically, most electrons which matter are electrons near the Fermi energy. When you measure the thermoelectric conductance, your quantum of conductance has changed, and what you are probing is different. Now you are looking at what occupied states offer to you minus what unoccupied states offer to you minus what occupied states are offering. And you can immediately see why your thermoelectric response can be either positive or negative. When you measure the thermal conductance, again, you are interested in electrons which have some entropy, and these guys are not exactly at the Fermi energy. They are a little above or a little below. And this is something to keep in mind when we are discussing different properties. And basically, if you do this in any of these formalism, there are two things which are unavoidable when you are degenerate. Again, we have a Fermi liquid, and we imagine that all interactions are going to show themselves in a renormalized mass. One is the Wiedemann-Franz law, and one is the Mott formula. The Wiedemann-Franz law actually connects the thermal and electrical conductivities to the fundamental constants, and the Mott formula establishes a relation between your thermoelectric response and the energy derivative of your conductivity. Now, Wiedemann-Franz law, you see, I tried to violate it, and I did not succeed. We have tried, we have thought at some point that it is maybe failing in some context. It is one of the oldest laws of physics, so it completely survived the quantum revolution, even if it was discovered 50 years after, half a century before. And it was first an observation, an empirical observation by these two gentlemen who found that if you look at different metals at room temperature and you just take the ratio of these two guys, there are not that much deviation. So you see, tungsten actually is a little different. I think there is some phonon contribution, but I am not even sure what's the explanation. But the order of magnitude within 20% is right. And after the quantum theory, and thanks to Sommerfeld, there is a proper expression for this. And it is a kind of cornerstone of Fermi liquid behavior. Now, during the last 2 decades, I should mention this because our community is sometimes forgetting something which happened. During the last 20 years, experimentalists try very hard to violate it in different contexts. So these are 2 different contexts. One is cuprate, the other is organics. In both cases, people were thinking about spin charge separation. This is a quantum critical scenario where a violation was also imagined at 0 temperature. But all of these subsequent works by other groups, same group, the papers were either retracted or they could not resist this, the test of time, let's say. I am not aware of any violation of the Wiedemann-Franz law at 0 temperature at this moment. I don't think anybody claims at this moment among experimentalists in 3D that Wiedemann-Franz is violated. Now, at finite temperature, it is very easy to violate it. But then there is an ambiguity. What is finite temperature and what is 0 temperature? We come to this at some point.
What do you mean 0 temperature?
So in the case of ytterbium rhodium to silicon 2, people have gone to 8 millikelvin. Okay? So this is one of the, what they can say that if they extrapolate it to 0, you see something which is within 10% the Wiedemann-Franz law. So what the experimentalists can say is that at temperatures which are basically the lowest we can go, if there is violation of Wiedemann-Franz law, it is within a window of 10%.
And the papers that you mentioned retracted, you mean the statement of
so here,
low temperatures?
No. Here there was a problem of actually radiation. This was an organic system at room temperature. This was a Lottinger liquid. The experiment, so these are careful experimentalists who found afterward that this was wrong. In the case of cuprates, there were a lot of fights, but I think Louis Teifer, who published the first data, now they claim that Wiedemann-Franz law is obeyed. So I think it's just made people aware that these are hard experiments, but there were controversies. It took years before people, in the case of ytterbium, rhodium, 2 silicon, 2, 4 different groups found exactly the same result, which is very good. Means that different labs found the same data, even if the interpretation can be different. But at the end, according to your bias, you can say Wiedemann-Franz law was violated by 10% or verified by 10%.
On the theoretical side, you have something that you have a material that's fully localized, but with a long-range interaction, long-term interaction. Couldn't you expect to be able to transfer heat over long distances without charge, without any charge conductance?
I am not making any statement about theoretical. In a Lottinger liquid, for example, spin charge separation should give you a huge violation of the Wiedemann-Franz law. What I'm just saying that in
3D.
Sorry?
You mentioned 3D.
Yes, exactly. What I'm saying that. So if somebody can do a proper 1D thermal transport measurement, most probably they are going to see this.
No, but I'm asking about the 3D.
No, in 3D, as far as I know, you can have whatever theoretical prediction. Nobody claims experimentally to see a 0 temperature deviation, violation. Okay, even, yes?
Your setting is about 3D, or because in 2D there are experimental results?
At 0 temperature?
Well, in the fractional quantum Hall effect.
Yes, yeah, okay.
No, but that's not
Okay, so yes.
systems where you have a superconductor.
No, but I'm talking about metals. You see, I am making a statement about metals, Fermi liquids, but even Fermi liquids very close to a quantum critical point. That is all my statement. Okay, but this is not, I think the interesting thing is that you can have finite temperature violation. And my main point, and actually we come back, this can be much more interesting. Up to now we thought that it is very banal, but it may be much more interesting than what we believed actually. So why in finite temperature you can have this? Actually, Andy mentioned small angle scattering, and this is what's going to happen. Small angle scattering, you see, it is known that these guys don't measure in the same way. If you are measuring your resistivity, you have always a pondering factor of 1 minus cosine theta. So in that sense, somehow the long mean free path of resistivity can be related to the fact that we have a lot of small angle scattering. Now, if you have small angle inelastic scattering, you immediately see that the energy and the momentum averaging would not happen to the same condition. So you see, small angle scattering is called sometimes, so I think Weizmann uses this word, a vertical scattering, because you go along the energy axis much more than along the momentum axis. Or you can say in this way that actually, in a vertical process, actually you don't go all around the Fermi surface, you just cross the line. This is very bad for thermal transport, but has almost no effect on electrical transport. And so this is state of the art, I should have gone for. So this is known for electron phonon scattering. And actually, the famous Bloch-Runeisen law, which gives you T5 resistivity in 3D and T4 in 2D, in 3D gives you a 3 cube resistivity. And the reason is basically that part of this strong T5 temperature dependence is because of the fact that the typical wave vector of phonons is changing with temperature. So the weight of small angle scattering at high temperature and low temperature is not the same, so something which affects electrical resistivity much more than thermal resistivity. The other thing, and this is maybe less well known, this is not something that you find in textbooks like Ashcroft or Weizmann, is that even electrical resistivity and thermal resistivity, both of them, the phase space is T square, but actually they don't scale with each other. So we expect to have Wiedemann-Franz law. So I'm not writing thermal resistivity in this way, WT, because it is actually the inverse of kappa over T. This is something which can be finite at low temperature, at 0 temperature. The whole point is that B and A are not necessarily equal because of the fact that small angle scattering is not the same for thermal and electrical transport, but at the same time, it doesn't change the temperature exponent because there is no change in the typical Q vector of your electrons. And this has been seen, for example, in this heavy fermion system. This is a work by Jean-Pierre Paglione and Louis Taillefer 10 years ago. And actually, we see it also in UB3. This is one of the subjects in my PhD, that you can see that t-squares are not the same, and there is a difference of factor of 2. So basically, it was known, but it was considered as a anecdotic information. So here is where the situation becomes interesting. So we talked about this several times. This paper was mentioned, that Gurzi was the person who, maybe began this reflection of what happens if we could get rid of Umklapp scattering. And then we have this paper, which was published in 2017, which appeared. And when I heard Claudia, you can imagine with all our backgrounds that do you recover the Wiedemann-Franz law? Because the claim of the paper is that you have a strong violation of the Wiedemann-Franz law. You are like less than, this is not a 10%, this is a 90% violation of the Wiedemann-Franz law. They cannot recover it up to or down to the lowest thing. And we said, okay, send us samples, we can measure it. So this is, I should say, these are very hard measurements, because these guys, so in Zurich, they try to measure microstructured samples, look at the thermal transport. And this is very hard, because to have a decent measure of thermal conductivity, you need to have a 4-point contact, means that you should be able to know your local temperature twice, 2 different positions, and you should be also able to quantify the amount of heat which is traveling inside the sample. Yes?
Does this measurement give you overall thermal conductivity or electronic thermal conductivity?
Well, you will see this material is so clean, very much like Andes, where we can forget phonons. All thermal conductivity is easy electronic. And actually, how we do not know it, because Wiedemann-Franz law tells us, and we know what should be the phonon contribution, is completely negligible. So you see, if you measure copper, for example, you have a very hard time seeing the thermal conductivity of phonons in copper, because electrons conduct heat so well that you see basically the thermal conductivity of electrons. This is true also in this material. Now, but what they measured is a 2-point contact. So I can tell you, they measured the thermal conductivity of electrons inside the sample, but they're measuring the thermal resistivity of the sample plus contacts. So this is the technical, if you want, objection, as we are going to discuss. So what we did, so what Alexandre did is to measure with this regular, 4-point contact, a decent crystal, which is 1 millimeter long. This is a hard experiment, because this system conducts very well. So the resistivity at low temperature is comparable to what Andy showed. This is 7 nanohm centimeter. So be ready to be surprised, because for me, 7 nanohm centimeter, you can, for an experimentalist, something which is below 1 micron centimeter is something very clean. In correlated materials, most of the time you should work with something much dirtier than this. When you approach nanohm centimeter, then you expect to have something extremely clean, but the setback is that thermal resistivity is very small, thermal conductivity is very large. This is why we have such error bars. But if we now plot L over L naught, so this is our data, and this is what was obtained on the mesoscopic sample. So 2 things. First of all, this is a strong deviation from Wiedemann-Franz law. So even now we don't know if this deviation is, the most plausible explanation is that they find a thermal conductivity which is unusually low, because they are measuring a thermal resistivity, which is the thermal resistivity of the sample plus contacts. But the other possibility is that there is a size dependence. And the lower you go in size, Wiedemann-Franz law violation becomes, we cannot rule this out. But this is the data I'm going to discuss about. And this is exactly what people see in cerium, cobalt, rhodium, indium 5. This is a strongly correlated system, or even in silver, where you have electron-phonon coupling. You recover Wiedemann-Franz law at low temperature, you recover it at high enough temperature, but in between, in this intermediate regime, where you have a lot of inelastic scattering, you have a deviation. What is remarkable about this system is the deviation is largest than what was considered as the ordinary kind of deviation you would expect in a metal. Now, where does it come from? So what we could see is that resistivity, so you can see here, so this is in nano-ohm centimeter, rho 0 is 7 nano-ohm centimeter, and then you have T square, and then you have T5. So it's a very nice system. It's unusual to be able to detect both T square term and T5 regimes. Because you see in copper, you have no problem detecting T5, but it's very hard to detect T square. In heavy fermions, you can easily detect T square, but it completely blows up the T5. In this system, accidentally, you can see both of them. You can even detect in thermal resistivity T square and T cube. So what we are doing here is that we take out the T square term and we plot the residual, after subtracting the residual resistivity and the T square term as a function of T5, and you see that it is a straight line. And you do the same thing for thermal resistivity, and you see it's a straight line as a function of T cube. So you can actually quantify all these terms. What appears is that the reason we have such a strong deviation is that the B2 term, the T square term of resistivity, is 5 times larger than the A2 term. If you look at the size of the T cube term of thermal resistivity, actually the ratios compared to A5 in WP2 and in silver does not matter. So in that sense, there is nothing particularly special about electron-phonon coupling in the system. Something is special about electron-electron coupling. Okay, this is our first diagnostic. If you can quantify the terms you expect, T cube, T5, and T2, you can ask, so why T in this system electron-electron scattering gives such different contributions to the thermal and electric transport? So you have two ways of going. Like every time, you have a conservative approach. The conservative approach is that it's all about a small q electron-electron scattering. You see, if you have a collision dependence which is has such a variation, strong variation with q, you can easily imagine that these collisions would give you a huge thermal resistivity, but they would not contribute to A2. So basically what we are saying is that inelastic mean free path for energy transport is much shorter than inelastic mean free path for momentum transport. So we are still in the Boltzmann picture, and it works. Now, not many systems have been put under this scrutiny. And during this research of all literature, we were thinking that WP2 is an extremely clean material, and we were right because it's 4 nanometer. But we discovered actually pure tungsten has a resistivity which is in pico-ohm centimeter. You see? So this is 60 pico-ohm centimeter. And actually, you can see these guys have measured A2 and B2. And actually, these two clean materials are those which show extremely different A2, unusually low A2 over B2 ratios. On the other hand, nickel, UBT3, cerium, cobalt, and indium-5, they have something where the difference is a factor of 2. So the question is, what sets this mismatch? So again, in the Boltzmann picture, there is a paper, there is an old paper by Herring, which says that actually the ratio should be quasi-universal and of the order of 0.4, and he had not that many data points in comparing it. But very recently, Dmitry Maslov has looked at this problem, and according to him, actually, you can have anything. So this is not really a violation of diffusive transport. The fact that these two guys can differ is all about long-range screening, and we cannot rule this out at all. Now, is there all of this has anything to do with hydrodynamics? Here is where we begin to have some light. Maybe there is something interesting happening here. Because if you come back to this idea of, okay, why we have electrical resistivity? So basically, electrical resistivity is T squared because this is the phase space of electron-electron scattering. But it seems that there are electron-electron scattering events which do not decay momentum. Because you see, if you consider this term is always larger than this one, so if we look at these two ratio, we would say that this is actually maybe a measure of momentum relaxing to momentum conserving collisions. So no, I'm forgetting that there could be a difference just because the small angle and large angle are not different. So in that case, there may be, at least a way of looking, is it possible to see hydrodynamic phenomenon in this system? Here I come back, you see, you should forget what I said in the beginning, and let's be very conservative and imagine that, normal scattering doesn't decay momentum. In other sense, let's forget what we saw in the case of strontium titanite. normally we don't expect normal scattering to decay momentum. Only umklapp scattering is going to decay momentum. So, and we know this, we come back to helium-3 in this context, so all T-square resistivity we are seeing in this system has something to do with these kind of scattering events. So, here is what has never been plotted in this way. People have known and actually have looked at this temperature dependence of thermal conductivity in normal helium liquid. And you know, these are plots of thermal conductivity in different regimes. And what is known is that at first approximation, it basically diverges as 1/T, but then there are corrections. And the reason you have 1/T thermal conductivity is really related to fermion-fermion scattering, which gives you a T-square, basically, phase space. Now, if you plot kappa/T as a function of T, you see that basically you have W2 as a function of T squared. It's just that they don't use the same terminology as we do. And now, if you put the thermal resistivity of helium-3 on a Kadowaki-Woods plot, you see that again we are another line. So you see this was already very messy, but let's now look just at the red points. The red point are the T-square resistivity of electrons and the T-square resistivity of helium-3. All of this is about entropy transport thanks to normal collisions between fermions. So the idea is that actually, so we don't have that much data. We only know that these two guys are low, but we don't know if it is intrinsic or has something to do with the fact that these are particularly pure. And here is where there is a hydrodynamic window, because let's now be very optimistic and say, let's take the rho zero. I'm doing exactly what Andy tried to test. If I take my resistivity in this sample, so this sample is still a little cleaner, so resistivity is 4 nanomcentimeter. And you find the same thing in the same values in thermal resistivity. If I translate this to a mean free path, this mean free path is of the sample of the size of the width of the sample. It's as long as 100 micrometer. So I can, from this value, have an idea what is the region which we can call ballistic. You see, the whole idea of ballistic is this hierarchy between the three scattering times. Momentum relaxing, momentum conserving, and boundary. So if I say that the boundary is where actually this rho zero value becomes smaller than, this T-square prefactor has a contribution to resistivity which is smaller than what is given by the boundary scattering, assuming that all of these 4 nanomcentimeter is coming from boundary scattering. Here is the ballistic regime. And of course, there is a regime where we are diffusive. And in between, there is a narrow window around 10K, where actually the Gurzi criterion is satisfied. But again, since this ratio was a factor of 5, by chance, we are in a region where the boundary is like twice lower than the momentum conserving collision rate and twice higher than the momentum relaxing waves. So,
Kamran, can I ask you? So
yes.
I didn't see, I think you were away when I talked. I'd read your paper before I came.
Mm-hmm.
And what I did was just the same game as you about power blocking, but you calculate the scattering rate and you use the known Fermi velocity to change it to a mean free path. That mean free path should be the absolute lower bound. That's as small as the mean free path can get to be a momentum.
Completely right.
Mean free path. And according to my estimates, it comes out of 400 microns at 10 Kelvin. Now, do you agree with that estimate or not?
I am not sure that I follow your. So if we take, so maybe I'm not sure that I understand you.
I'm saying that.
If I take 4 nanomcentimeter and I use just the root formula, taking the.
I'm saying let's forget the residual resistivity. Let's just look at the electron-electron length, and I think it's about 400 microns at 10 Kelvin. So if it's about 400 microns at 10 Kelvin, you're in the ballistic region at any device size that anybody ever works with in the material.
Yeah, but okay, but here is, I will try to answer your question after the next slide.
Okay.
Because here I am assuming that there is no impurity. You see, I'm assuming that, because there are 3 scattering times, I'm assuming that what gives me 4 is basically the sample size. If I had a sample 10 times bigger, I had a resistivity 10 times smaller.
Yeah, but I'm asking you, as I'm saying, I believe I'm saying a separate thing, right? The sample size is
Yes.
something in principle you've got control over. But if the fundamental lower bound on the electron-electron length of your temperature of measurement is 0.5 millimeter, you are never going to be able to do a hydrodynamic measurement with a sample which is of scale microns.
Yeah.
Full stop.
Can I continue? Because I come back to this afterward. I'm not sure that I get your point exactly. It's because this will completely change as soon as we imagine that half of the, this resistivity is coming from impurities. So I'm not sure that we are talking the same language.
We'll talk after.
Okay, so the whole idea is that this, as soon as imagining that half of this resistivity is coming from impurity scattering, actually there is no hydrodynamic window. So here it was the situation, the ideal situation, which was here, and within a factor of 2, the whole thing vanishes. But I guess that this is not your point. What?
That's not my point, but
Yes.
we can talk separately.
Okay.
about my point.
So the whole point, coming back to this, we are, though, I arrived to my summary. I think the most important part of actually my talk is this, because this was not plotted before. And one thing about helium-3 is that, you see, in metals, we can never get rid of momentum relaxing events. In helium, actually, besides impurity, which are negligible, there is no momentum relaxing event. So, and actually, viscosity of helium-3 has been measured. It is known. It is known that actually this viscosity increases as you go to lower temperature. Now, the whole question is, if we can see any size variance of this A2 over B2 regime, this would be, so I come back to this. If we see that if you change the sample size by a factor of 10, going towards the lower dimensions or higher dimensions, this number changes. This, I think, is something you cannot explain in the Boltzmann picture just by invoking small angle versus high angle scattering. At the moment, I am not aware of any way of finding a scenario in which this ratio would be correlated with sample size. But again, the story is not finished. So let's come back to this. Wiedemann-Franz law, again, was recovered at very low temperature, but there is a deviation. So in that sense, the Dresden group was right, save for tungsten, which is also an ultra-pure material. Such deviation of the Wiedemann-Franz law at finite temperature has never been observed in any system. It is caused by electron scattering. This we know because we can separate T square and T3 contributions. So the first explanation would be that, okay, we have a system in which we have a small angle collisions, and that would be the end of the story. But of course, we cannot rule out that hydrodynamics plays a role, and thank you for your attention.
So if you say that it's an ultra-pure material, is there direct evidence for that?
No, well, you see, what I can tell you, having a residual resistivity of 4 nanohm centimeter, that means that the mean free path of your electrons are very long. That said, when your carrier density is 1019, it is not that difficult to have a level of disorder in which electrons can travel a long distance before being scattered. I gave you the example of pure tungsten. You see, bismuth has a very long mean free path. Crystals of bismuth can have a mean free path as long as 100 micrometer. Antimony has a higher density, so bismuth has 1017 electrons per cubic centimeter. In antimony, you have 1019. Tungsten or tungsten diphosphide have 1020. So they are still far from one reason that you can get long mean free passes compared to copper or compared to dolophossites is just because we are cheating. we have electrons which are much bigger, so much harder to be scattered. So this is not a statement about chemical purity, but from electronic point of view, actually you can do mesoscopic physics with samples which are above micronic. But this was known in the case of bismuth, for example.
The mean free path is longer than that of the phosphites?
No, because
It's about the same number, no?
no, actually, yes, because it's very easy to because the details are important. But at first level of approximation, and these samples have 100 times more electrons. The residual resistivity is comparable, a few nanomcentimeter. So you can say that the mean free path should be longer.
Yeah.
But this is just forgetting any anisotropy, dimensionality, everything. So you see, if in copper, if you have ultra pure samples, you can reach nanomcentimeter. But the lower the density is, it is easier to get mean free passes, but that translates to higher residual resistivities.
So this material WP2, it has actually very strong electron-proton coupling, right? I remember reading it somewhere.
You can read it, but again, if I compare, you see, I'm an experimentalist. Actually, one of the interesting things, okay, I can tell you something very interesting about this system.
But, I mean, wait, actually, I meant to ask a question, not just to make a statement that I read something. So why are you then, I mean, if that's true, or why are you not seeing all this phonon drag stuff that Indy talked about?
You see, phonon drag, you see, I have been obsessed with thermoelectricity during the last 30 years. Phonon drag is when we don't understand, and it should be there. There is some, so in copper you have phonon drag. Okay, so you should have a strong electron-phonon coupling. But there is no superconductivity in copper. Okay, so what in this system, actually, we didn't look at thermoelectricity very carefully, but I would not be surprised to see phonon drag in thermal power. Normally, the systems which do not show phonon drag are rare. There are some of them, but that doesn't mean anything. So the statement I'm making is that the T cube term of thermal conductivity due to phonon-electron scattering compared to T5 term of electron-phonon scattering in electrical resistivity has the same ratio as in noble metals. So this is a very precise statement about what we can measure. But I don't know if electron-phonon coupling is strong or weak in the system. What I can say that the system is pure enough not to be worried about phonons, because we have measured other semi-metals like antimony, but then you have a large phonon contribution to thermal conductivity. So you should get rid of this. So these are small details which make a little difference.
So is there any difference between electron-electron collisions because they interact, or electron-electron collisions which are mediated by phonons, for example? Is there a way to differentiate between them? Do you know this?
As I am not, even this difference, this considerable difference between T squared thermal resistivity and T squared electrical resistivity of this amount was a surprise for us. I was thinking that these two numbers are different but close to each other because of only two cases we knew in. So we should study them more. But I don't know. I don't know how to answer your question in an accurate way.
Gotta try again. So to get the hydrodynamic condition, as we all agree, you need a momentum conserving length which is less than the momentum relaxing length.
Yes.
Right? And maybe, say at 10, 20 Kelvin, you can achieve that in this material, right? That's fine. But you then also need, in order to observe it, you need to set up conditions where you have a device of a certain width, and if you want to observe the Poisson regime, you need your device width to be of order, I don't know, 5, 10 times the microscopic length scales. My problem is that because this is a good metal, when I just put in the numbers for the maximum electron-electron scattering rate, before we start arguing about any angle of scattering, just the total.
Okay, can I ask you a question? Are you talking about
hundreds of microns at 10 Kelvin in tungsten diphosphide?
But which electron-electron scattering are you talking about?
I'm talking about just using the
momentum conserving or momentum?
you see, But the point is, so in a normal thing, you calculate a number which is the maximum scattering rate it could be, and then you start arguing among yourself and your friends about an UCLAP efficiency to see what the ratio is. But even before you start caring about that, the rate is incredibly low at 10 Kelvin if you have a 3000 Kelvin Fermi temperature.
No, but Andy, I try to answer your question because it seems to me something should be clarified. Look at this curve. Okay, it's all here. Here we are at 4Tk. Okay, this is 160, no, not 40, maybe 12 Kelvin. Okay, this is where you are. So this is C square. Okay, this is the residual resistivity. This is the amount of momentum conserving events. So you know you should conserve. All these guys are of the same order of magnitude. This guy is of the order of this guy, but this guy is 5 times larger than the other.
Very good, very good.
So that's all.
But that's telling you that if you like, the right experiment, there may be a viscous term to observe, right?
Mm-hmm.
But if those lengths, so let's go to a completely different universe where you've got the right hierarchy, but one of your lengths is a kilometer and the other one is 10 kilometers. You are not going to be able to do an experiment on the scale of microns and observe that. You're going to be in the ballistic regime. And that's the point I'm trying to make. According to the numbers I was able to produce, any realistic experiment which is being done with micron width samples is being done in samples which are much narrower than any of the microscopic length scales. And therefore, it's very hard for me to see how electron-electron scattering explains an observation in the Poisson regime. That's the point.
Okay, okay. Now I understand that. Now I think I got your point because I was not addressing that question. You know, if you can observe Poisson flow in these samples. The question I was trying to address, but I'm not sure, actually I know the answer, is that does the existence of momentum conserving events play a role in this magnitude of deviation from Wiedemann-Franz law in macroscopic samples, which was what was proposed on that paper. We cannot rule it out. There may be, because nobody knows, but that doesn't mean this is Poisson flow. Or we can do Poisson flow in structure samples. I get your point.
In the end, it was also a question. The question really is, do you agree with the estimates I was making? But let's talk about that afterwards.
Okay.
I think that paper that you're referring to actually also made a statement about scaling of the resistance with sample dimension.
Yeah, but that, if you you see, you heard Andy. You see, I want to make now a general statement. So Andy was very careful about the science paper, but if you look at the science paper, it was a very subtle deviation. They changed the sample size by a factor of 75, and the expectation of the Boltzmann theory was violated by something like 30%. Okay, so I cannot rule out that such a thing maybe happen here. So he just had the argument that they may not happen. But we are talking about a violation by a factor of 10 of the Wiedemann-Franz law, which we saw that experimentally it is most probably not correct. And again, we come back to maybe subtle corrections to what is the Boltzmann picture. So if you change the sample size, of course the resistivity will change. But this, any experimentalist can tell you it is because of the size effect. You see, if I take this sample, makes it 10 times larger, of course, resistivity is expected to be 10 times lower. This is not surprising. This is what we see every day in bismuth when you do thermal conductivity measurements. So, you know, this is really something very important. There should be some deviations, but these deviations are very subtle. And in that paper, it was not at the level of analysis. But there were other features like magnetoresistance. You know, I'm not saying that. I'm just addressing this thermal conductivity because the Wiedemann-Franz law is something which caught our eyes.
Okay. There was a question. Question. Short question. Would it be possible to do the same measurement with graphene also?
It's very hard to measure thermal conductivity of graphene. But maybe I can make a comment. You see, Philip Kim has a paper on graphene. But you see, again, there is a violation of Wiedemann-Franz law at finite temperature. And you see, if you ask me, you have semiconductors in which you can have what people call unbipolar heat transport by electrons and holes. People knew in semiconductor community that you can have this kind of violation of Wiedemann-Franz law. They didn't call it hydrodynamic. And I am not sure to what level. You see, so the experiment is most probably correct, but maybe also the interpretation. The whole question is having a big unbipolar flow of electrons and holes is something which, which may be hydrodynamic. You can call it hydrodynamic, but something equivalent is expected in conventional transport theory. So that doesn't violate anything, and they recover the Wiedemann-Franz at 0 temperature, and everything is fine.
Okay, if there are no more questions, let's thank Kamran again.